This presentation is on partial F-test. I'm Pat Obi at Purdue University Calumet. In this presentation, we show how to test portions of a regression model, which is a case where one regression model, called the reduced model right here, is nested within a larger one, which is called the complete model. And so here we wish to determine which of the two models fits the data better. But we have to be mindful of the fact, though, that in all cases, really, the complete model, which is the blue model right here, would always have the higher explanatory power measured by the coefficient of determination r squared, and the lower unexplained variation measured by the by the sum of squares error, and also, if you like, the standard error of the estimate. Keep in mind, standard error of the estimate is the square root of the mean square error, and the mean square error is the sum of squares error divided by the corresponding degrees of freedom. Alright, so the key question here, though, is, while we know that this complete model is going to have the higher r square and is going to also have the lower unexplained variation measured by SSE, sum of squares error, the question is whether this decrease in SSE in the complete model is statistically significant and not merely due to the addition of these terms right here, or for that matter, due to chance. So to help explain the concept behind this, I provide a quick example here where we're investigating the relationship between the cost of shipment and the variables we believe impact the cost of shipping for this firm. And the variables are x1, which is the weight of the shipment, and x2, which is the distance that the shipment has traveled. Additionally, we're introducing three transformations here, three terms. The first is an interaction term, x1 times x2, which is a way of trying to capture the combined effect, if that exists, of distance and weight. In other words, when a package goes quite a ways away, a longer distance, given its weight, does the combined effect of weight and distance impose an extra measure of cost consideration with respect to the package, if you like? And then the quadratic terms right here measure the curvature in the response surface, and so they are trying to capture the curvilinear relationship that may exist between shipping cost and weight of shipments as well as distance, telling us that perhaps cost does not go up monotonically as weight and distance increase. So this is the complete model, and we're going to compare the quality of this model to this reduced model, because if this reduced model is sufficient, then we'll stay with it since it is more parsimonious. So here's the data set. We're going to regress y, shipping cost, against all of these five independent variables, as it were, and then separately we're going to regress y on the red columns, which is the reduced model. Here are the results. I've shown how to use Excel to perform a multiple regression in a different presentation. So this is the reduced model, and as you can see, the model is statistically significant. Look at the very extremely low p-value. Also, about 98.5% of the variation in shipping cost is explained by this entire model, which is pretty decent. Now then, if we go to step 2 and run a regression on the complete model, we find that yet again, of course, f remains significant, but observe that the coefficient of determination, which is a measure of the proportion of the variation in y that has been explained by the entire model, has increased. I go back here from 98.5% to, go forward, 99.4%. As well, we find, going backward, that the sum of squares error has decreased from 6.63 to 2.74. So these are good things. But the question is this decrease from 6.63 to 2.74 statistically significant? This is the question that we pursue in this partial F-test analysis. So to answer the question, we construct the test statistic, which has an F distribution. The numerator is a ratio, the denominator is also a ratio. SSER is sum of squares error in the reduced model, while SSEC is sum of squares error in the complete model, and these are the substituted values. K star right here is the number of additional coefficients in the complete model. So if I go back right here, you find that we have two additional coefficients, B4 and B5, in the complete model, and that's the two that you see right here. So then we divide this whole shebang right here by the sum of squares error in the complete model, which we go back here and we just pick it up from this. That's why I highlighted them already. And then we divide by n minus k sub c degrees of freedom, where n is the sample size. Total sample size in this study is 20 observations. Kc is the number of coefficients in the complete model. And if I go right back here again, well, this is the complete model. We have b sub 0, 1, b1, 2, 3, 4, 5, and 6. That's it. So there are 6 of those. 20 minus 6 is 14. So 2 degrees of freedom in the numerator and 14 degrees of freedom in the denominator. So anyways, working this out, we find a calculated F of 9.92. To this, we must compare the critical value of F based on 2 degrees of freedom in the numerator and 14 in the denominator. And here is the F table actually. Alright, so these are the degrees of freedom in the numerator and these are in the denominator. So 2 above and 14 below, and that's the value right here, 3.74. So that's the critical value right here of F. So as you can see, since the calculated F value exceeds the critical value, we must reject the null hypothesis that there is no additional reduction, there is no significant reduction by the introduction of those two curvature terms, these two terms right here, and accept the alternative that the introduction of these two curvature terms does in fact significantly reduce the unexplained variation in the model measured by sum of squares error. So in effect, we are concluding that these quadratic terms here do contribute information in the prediction of shipping costs and therefore should be retained in the model.